Hi, thank you for having me. It's a real pleasure being here. The title of my thesis is called Causal Inference for Social and Engineering Systems. So the key framing question that kind of motivates us all of this work is a very simple one. Is what will happen to Y if we do A? Y is some outcome of interest and A is some action that we can take. And many interesting questions across a variety of fields can be posed in that simple way. For example, in healthcare, you could ask, what will happen to a patient's health if they're given a new drug? Patient's health is the outcome of interest, and the drug is the action that they could take. In policymaking, you could ask, for example, what will happen to the number of COVID-19 infections? Let's say a new social distancing policy is introduced. Or say in engineering, which is close to my heart, you can ask, what will happen to say a data center's latency if a new congestion control policy is introduced? And these kinds of questions, which are clearly very important across these fields, what you really need to understand is the causal effect that A has on Y. So how do I go about doing that? It's by bridging two fields. One is causal inference and econometrics, and the other one being machine learning. Why? Because causal inference and econometrics thinks very carefully about how do you do causal reasoning despite having unmeasured confounding. That's what we mean when we say correlation doesn't equal causation. It's really confounding. And there's a variety of very beautiful frameworks that have come out of it. For example, instrumental variables, regression discontinuities, difference and differences, and all of them, what they're doing is looking for natural experiments that are happening all around the world to learn these causal relationships. But generally, the estimators that have come out of it have been designed for small economic data sets. On the other hand, you have machine learning, which thinks very carefully about prediction with modern data sets. It can be high dimensional, noisy, and sparse. And many frameworks such as high dimensional regression, kernel methods, neural networks, what have you, have come out to deal with that. But they're generally not designed to handle confounding. And so what I am focused on is to bridge these fields to get the best out of both of these worlds. Specifically, my work's been about bridging two subfields. The one is synthetic controls, which are the core idea in econometrics. It tries to answer the question of what if an intervention did not occur? What happens if someone had remained under control? And try to bridge that with matrix and tensor completion, which is the core idea in EECS, stats, machine learning, that tries to impute missing data in a matrix or a tensor. And so my work's been about two parts. The first is called synthetic interventions, which brings ideas from tensor completion to synthetic controls. In doing so, we address the unresolved problem of counterfactuals and the presence of interventions within the synthetic controls framework, as laid out by Alberto Abadi in his 2020 review paper. And the second one is causal matrix completion, which now takes ideas actually from synthetic controls and brings them to matrix completion. And in doing so, we try to address the unresolved problem of matrix completion with missing not at random data, as laid out by Ma and Chen in 2019, who are at Carnegie Mellon. Let me start with some work we did in synthetic interventions. So synthetic interventions is really about how do you do counterfactual reasoning via tensor completion. For example, say in medicine, you're collecting data of different patients over time. Rows would be different patients, columns would be different time points, and different slices would be different drugs. And each entry of this tensor would be some health metric of interest, for example, say tumor size. Because you can obviously only observe each patient under one drug at a time, you get a very sparse snapshot of this tensor. You get this block sparse tensor. And so a meaningful counterfactual question could be, say, what if the patients who had gotten the green drug had instead gotten the blue drug? That would really correspond to filling out the shaded blue part of the tensor on the right-hand side. And that's exactly what synthetic interventions lets you do. For example, in engineering, you could ask, you have data centers, rows would be different data centers now, columns would again be say different time points, and different slices would be different congestion control policies. You can ask the question, what are data centers who got the blue congestion control policy now instead got the green congestion control policy? That would again correspond to just filling out the shaded green part of the tensor on the right-hand side. And that's again what synthetic interventions lets you do. And so you can see is that these different kinds of studies are really characterized by unique sparsity patterns. And one of the key questions of causal inference, which is estimating counterfactuals, really corresponds to tensor completion. And this is no coincidence. It's really about this, these two fields ask the same questions, they just have a different language. For example, causal inference, many of us say, well, it's just a missing data problem. And those of us in ML say, well, tensor completion is a missing data problem. And there's core ideas in both of them that have a one-to-one mapping. For example, the notion of different experimental and observational studies. They really amount to having different sparsity patterns in the induced tensor. The notion of estimating counterfactual potential outcomes, that really amounts to computing specific missing entries of your tensor. And the notion of confounding, which is what plagues causal inference, you can really write that down as a problem of missing not at random data in your tensor. Okay, so there's one thing I hope to leave you with conceptually is that there's deep relationships between these two fields. And what I've been excited about synthetic interventions is that we've widely used it across a variety of social and engineering systems. For example, the work I'm probably most proud of is work we've been doing with Tarak Therapeutics, which is an Alzheimer's company. So they gave us access to their phase 3 clinical trial data that had failed and cost them, it ran for over 2 years, cost them almost $500 million. And the average treatment effect of all the therapies that they tried was ineffective, was insignificant. And so the question we were exploring with them was that maybe there's a subset of patients that the therapy was effective on. And this is the type of tensor that was induced here. And what we did is we filled out the right-hand side of this tensor. That is, for each patient, we created a synthetic trajectory of what would have happened to them under every drug. And what we actually found through this procedure was that actually 20% of patients could be potentially responsive. So all was not lost. And this is being now used to guide the next phase of clinical trials. And they've been so excited about it that we've jointly filed a patent with them on it. I also currently consult for Uber Technologies. And the question they had for us was that what would passenger wait times be if US cities adopted routing policies that have been used in Brazil? And again, you have this tensor. It's a little bit different now because you get the staircase pattern because different cities adopted the policy at different time points. And again, what we found by this kind of tensor completion perspective was that larger US cities would see the greatest increase in wait time. And because these kinds of A/B tests are run all the time in Uber Technologies, they're trying to use the synthetic interventions framework in their production systems as we speak. And across a variety of applications, including with the Poverty Action Lab at MIT, some COVID-19 policy evaluation. With Caroline Uller, we've been thinking about using it at the Broad on drug design. And with Dream 11, which is a large e-commerce company that thinks about fantasy sports and cricket in India. And in terms of theoretical results, what you can show is that the counterfactual trajectories you get for each unit under each intervention, that's finite sample consistent with the true counterfactual trajectory. And you can also prove asymptotic normality results, which lets you produce confidence intervals. The key structure you need is that the underlying tensor that's induced is low rank. That's really what lets you share information across units, time, and interventions. Now I'm going to spend a little bit of time talking about matrix completion. So matrix completion sometimes get a bad rap. People think it's just recommendation systems, where rows are users, columns are items, and you want to fill in the ratings. But it's a lot more than that. For example, it can encode regression discontinuity, which is, imagine Medicare, where you get Medicare at age 65, that kind of leads to the staircase pattern. Or even say in contextual bandits, think of rows as different states, columns as different actions, and each element is being the reward for a given state and action. Right, so the goal across these applications is imputing missing entries and denoising observed entries. And the impediment to a unified approach is that different applications have very different sparsity patterns. So our main contribution here is a unified approach that works across both empirically and theoretically across these variety of sparsity patterns. The algorithm that we propose is called synthetic nearest neighbors. It brings together synthetic interventions with nearest neighbors, or collaborative filtering known more colloquially. And the theoretical results we produce is entry-wise finite sample consistency and asymptotic normality. And in general, most recovery results in matrix completion are in the Frobenius norm. What we prove is an entry-wise guarantee. So what do I want to do with assignments? One slide on it. I think the one thing that keeps me up at night nowadays is how do you build causal simulators for reinforcement learning? We've heard so much about reinforcement learning over the past day. I think one fundamental assumption that's being made a lot of the times is that you have a simulator. What is a simulator? It's an oracle that helps you answer the question, what if some agent N took an action A at state S? What's the next state? You need a simulator that tells you that answer. But to me, this is fundamentally a causal question. So where have we seen the greatest success of reinforcement learning so far? Well, it's board and video games where you have the simulator for free. Or it's in places like the OpenAI gym or robotics where you have to painstakingly build a simulator with your knowledge of physics, say. So I think a key challenge to the widespread use of reinforcement learning is creating such simulators for complex cyber-physical systems, say the electric grid, or data centers, or healthcare policymaking. The question I have is, can we build causal simulators for reinforcement learning using historical data? What I mean by that is offline data, where I only get, say, historical patient records of previous state action tuples, and fundamentally, you cannot experiment with your system. And so what I call it causal, because it could be observational data. That is, there could be a latent confounder that affects both the state transition dynamics and the action that's picked. And for those of you who are familiar with the Markov decision process literature, in MDPs, you normally assume that the action is still only a function of observed state. What makes it a causal problem is now the action itself can be a function of unobserved latent state. Okay. So two works I've done initially on this. One is called PerSim, which is about building simulators despite having one observational trajectory per agent. And on the more theoretical side, I've been thinking about formal analysis of observational linear dynamical systems. And thank you very much.
Anish. It seems like in some cases there's some information limits, like I can construct two different causal relationships between some number of variables such that the observations you gather are identical. I mean, so like it seems like conceptually, what's the way around that problem?
In some sense, that is being captured by the latent factors that define the tensor. And what we're not trying to estimate is those latent factors. We're not trying to identify those. So as long as the different latent factors give you the same outcome, it doesn't matter because we're trying to, it's up to rotational invariance, it doesn't matter. Because our object of study is the outcome itself, not the latent factors that define the outcome. I see. Yeah.
Yeah, so when you're doing this kind of data imputation approach, you're using the low rankness of the tensor as a way of choosing what to impute there.
Yeah.
But presumably you still have other choices to make. You can't just use low rank as a way of choosing between what your sort of inductive bias is. So how do you choose between different low rank completions?
So we don't try to do this global estimator. In general, if you try to do like find me the best low rank fit that fits your data, those generally don't work with global estimators. They tend to be very, very sensitive to the missingness pattern. What we try to do is a very local perspective, like a nearest neighbor style thing.
Right.
And then those you actually get unique answers. Okay. There's only one answer that you can get in that sense. But yeah.